Okay, so I'm Brian. I'm here. I'm finally set up. Thank you for your patience. I'm going to talk to you about CircuitPython, how to write drivers with it, why you would want to do that. So here you go. So some bits about me. My name is Bryan. I work as a developer, hardware engineer, all kinds of stuff for Adafruit. For the first 15 years or so of my professional life, I was a web developer. Did 3 years or so in Python way back when, then 9 or more years of Ruby on Rails after that. After a while, I started just kind of getting tired of it, wanting to try something new. So I picked up a new hobby, kind of picked up an old hobby, working with microcontrollers, electronics, stuff like that. So I've always been into hardware. I've always been into like down in-depth stuff. It's just been, I was just one of those guys that would take stuff apart and not be able to put it back together. So I picked up this hobby again, and this old new hobby turned into a new jobby. That slide didn't work out. Oh well. So yeah, I started doing hardware a lot in my free time. I started contributing to Adafruit projects, and eventually they hired me. And so I was able to ditch my web dev job and do hardware full time. It's like super dream job. I was super excited. Yay! Yeah. So why are you here? Why are you listening to me? Learning new stuff is cool. Everybody likes learning new stuff. You know, I'm going to be talking about hardware, microcontrollers, stuff that if you guys are primarily data scientists or other type of Python users, you might not have experience with. You're going to learn new things to use with your existing skills. Why CircuitPython specifically? CircuitPython has an amazing community built around it. This is something that Adafruit puts a lot of time and effort into. And it was my first experience doing open source contributions, and it was amazing at that. The community is there to help anybody that wants to contribute, regardless of technical skill, background, or anything like that. If you just want to learn how to fix typos on GitHub, we'll show you how if you don't know how to, all the way down to if you want to get straight into the core of the core C code in CircuitPython, you can help with that too. So great for open source. Drivers specifically, because drivers are in some sense at the core of what makes CircuitPython awesome. We've got, I don't know, hundreds of drivers at this point. For just about every piece of hardware that we sell at Adafruit, we have a driver for it so you can use it from CircuitPython. It makes picking up hardware really easy. So drivers are super important. What are you going to learn? What CircuitPython is? That's pretty straightforward. Why hardware is super awesome. The fundamentals of how drivers work, specifically embedded drivers for sensors and stuff like that. We're going to learn a bit of bit math. And yeah, that's it. So things that you aren't going to learn. We're not going to learn low-level details like bus protocols and stuff like that. We're not going to get into the core of how CircuitPython works. That's a whole nother talk. And you're not going to learn everything about CircuitPython. You're going to learn a subset that's enough to just get your feet wet and hopefully get you interested. And you're not going to be writing a driver for your fancy new graphics card. That's just not going to happen. So what is CircuitPython? CircuitPython is a fork of MicroPython that was written by Damien George. He is a sweet Australian dude who one day decided, hey, I bet I can fit Python on a microcontroller. Spent a bunch of time, got some funding from a Kickstarter selling a board to run it, and a bit later we had MicroPython. It's Python, right? So all of the great things about Python, why you use Python, fast iteration times, lots of tools available to you. All of those things can be applied to hardware, microcontrollers, and stuff like that. And that improves the process of writing for microcontrollers much more than the status quo. So yeah, it runs on microcontrollers. Microcontrollers are essentially teeny tiny little computers about the complexity of a C64, a Commodore 64, or some of the old 8-bit computers. They've now fully surpassed that, but in terms of orders of magnitude, that's about where they're at. Our boards run from anywhere from 8 to 120 megahertz, as opposed to gigahertz and whatnot. Though they are getting quicker up into the 600 megahertz for the fancier ones. CircuitPython is focused on people learning. We said learners specifically because it doesn't matter if you're young or old, new to programming or not. Really, the key focus for CircuitPython that differentiates it from MicroPython is that everything we do is targeted towards using hardware to teach writing software to people who have never done it before. So that's kind of our MO. So how awesome is CircuitPython? How cool is it? Like I said, it's Python. You get all those fun tools and styles of writing software that you get from using Python. It's a higher level interpreted language, so all the fun stuff that comes with that. You don't have to compile your code. I mean, you have to compile CircuitPython to get it on there, but that's easy peasy. And we'll do that part for you. Most embedded development, you have to compile. Pretty much, there's one or two other examples of languages for microcontrollers that are interpreted, but there aren't many. The most places you're going to be writing in C or C++. Arduino, you may have heard of. It's basically C++ with some fuzz around it. So no compiling your code. That means faster iteration times. A CircuitPython device mounts as a USB drive, right? So you plug a CircuitPython device into your computer. It shows up as a CircuitPy drive, just like a thumbstick or something. And you can copy your source files onto it. It will automatically reload files, and you're running and going. If you've ever worked with microcontrollers before, it's so much better. So much better. I cannot yeah, you'll just have to see it for yourself. It has a serial REPL. So the REPL, when you type Python, you can go in and type Python commands and it will read, execute, P and L it also. Print loop this, there you go. So you can have interactive working with CircuitPython, and you're talking to the hardware on the device. It's like a real-time, I don't know, powwow with the hardware. It's pretty sweet. Cool. So I'm gonna try and do a demo now. So let me figure out how I want to do this. I need to exit here. Of course, that's over there. Moo. Where's Moo? This is Moo. If I can get to it and get it back on my window, because everything wants to go over there. So let's get this over here. Okay. This is a Circuit Playground Express. It's our go-to beginner board. If you were at PyCon 2019, you got one in your swag bag. This is our perfect starter board because it's got a whole bunch of sensors and stuff already built into it. You don't have to solder anything. It's got 10 neopixels, which are RGB LEDs. It's got a accelerometer that can sense orientation, a light sensor, temperature sensor, all kinds of stuff to play with. So that's why we suggest this one. So I've got a demo sketch loaded on there. And let me see. Okay, so here it is. All 10 neopixels are lit up, full brightness, retina searing, awesomeness. So each neopixel has 3 LEDs in it. It's got a red one, a green one, and a blue one, as you would suggest. And the code's told all of them to turn on at full brightness. Where did that go? That's not what I wanted. That's not what I wanted at all. Moo. Hello, moo. It crashed. Awesome. Moo crashes sometimes. We suggest moo for beginners because it's got the serial REPL built in. I am going to move so I can code and talk at the same time. No, that's not going to work out so well. Okay, well. So, you guys can see the code now. Up at the top, we're importing board. Board is kind of a representation of all the hardware that's on the board that you're talking about. We're importing a NeoPixel library. That one's built into the core of CircuitPython because just about every board we sell uses it. And then we're also importing time because looping. So we're not doing much in that loop right now, but you can see on line 5, I am creating a NeoPixel object and specifying which pin it's on. Board.neopixel is just another name for the pin that the NeoPixels are attached to. And I'm saying that there's 10 NeoPixels. So, if I can, maybe that will help. Yes, that's a brilliant idea. Okay, where'd it go? Moo, here you are. What? So can you see it now? Yeah, I can. Yep. Yeah. Okay, so cool. Awesome. So here we're saying pixels.fill. Fill takes the value that you give it and sends it to every NeoPixel on the chain. Side note, NeoPixels are cool because, you have 10 RGB LEDs. Normally, that would take 10 times 3 data lines or things to adjust the voltage to the individual LEDs. NeoPixels have positive voltage, ground, which you need for everything in electronics, and then a single shared data and clock line. So one single, three lines coming out of your microcontroller, you can control hundreds of LEDs. So to further explain, we're saying NeoPixels.fill, and we're giving it RGB values. So we're saying 255 red, green, and blue. And if I take this and change this one to a 5 and just hit save, it saves, auto restarts, and the color is different now. I'm gonna go do a little, actually use this time thing here. Actually, we want both of these. I'm gonna copy this, paste it down here, change that to a 0 so we get a different color, and hopefully maybe this will flash. Yay, woo, changing colors. Huh? Yeah. I guess, yeah. Cool, so it's really that easy. A couple keystrokes, you're changing your code, it's Python, right? So you're constantly iterating, constantly doing fun new stuff. That is my demo. Okay, let's see if I can get back to my slides. Hello, separate display. Am I gonna keep my stuff? Yay, it worked. Cursor, thank you. I'm gonna unplug this so it stops distracting me. Okay, cool. So that was a demo. So what is a driver? A driver is a piece of hardware that talks directly, or it's a piece of software rather, that talks directly to hardware and abstracts it. Drivers are a type of what's called firmware. Firmware is that ooey gooey middle between software and hardware. Drivers are drivers, right? So this is a metaphor I like to use. If you're thinking about someone giving you a Lyft ride, you as the passenger are the client software. The car is the piece of hardware that you're talking to, and the driver driving the car for you is the driver, right? So you talk to the driver, you say, hey driver, please take me to the conference center so I don't miss my talk. And he says, okay. Driver knows all about turning the steering wheel, pressing gas, forgetting to use his turn signals, all that fun stuff. Drivers are bridges. It's kind of a metaphor, but it's a bridge in the sense that it's kind of the bridge between the hardware and the software, right? So it facilitates the communication between the two abstracts it so that they can have their separate domains that they care about, and whatnot. So some people might say, okay, so is it really a bridge between software and hardware? Well, isn't that what the OS does? Kind of yes, kind of no. OSs use drivers to interact with the hardware, so really it's the same thing. More metaphorically, a driver is a bridge in that it opens up new domains that you can apply your software skills to, right? So once you stop talking about purely software and start interacting with the real world, all kinds of fun new stuff opens up. Okay, so raise your hand if you've ever tried to explain the software that you write to a non-technical person and had their eyes glaze over within 15 seconds. Right, that's just how it is, right? Not everybody's familiar with how software works. They have all this context that they would have to load in to really understand what you're talking about. Hardware is different, right? It's right here, it's right in front of you. You can see and feel what's happening with it, right? You can say, if I program this with a button to change the neopixels, you can see, I press this button, the neopixels change, right? It makes stuff, hardware is making stuff that does things, right? Yeah, of course your software actually does things, but does things in the sense that most people will understand, right? It's very grokkable and understandable by normal lay people. So, this is a GPS module. It's pretty sweet. It's got everything you need to, it does all the hardware bits of GPS for you. This particular one is set up to be plugged into your computer over USB. We've got ones for working with microcontrollers. I should have gotten a different picture. Oh well. So, big thing about hardware and why it's super cool is sensors. And I am supposed to have pictures of lots of stuff, but I don't because I'm slow. And I procrastinated. But there's all kinds of stuff that you can add to your the capabilities of whatever project you're doing by having access to all these different types of stuff, sensors. Different modes of sensing that you can have access to. Visual sensing, we've got proximity sensors that measure proximity, obviously, light sensors, small infrared cameras, anywhere from 8x8 to, I think there's one 32x32, IR pixels that you can talk to with Python. It's pretty sweet. Gesture sensors, this is a new one that I'm working on. It's like a proximity sensor in that it's got an IR LED that it shines out, but instead of just a simple sensor, it's got a small camera in it, so it can actually see things moving around. That one's still in progress, but is going to be super sweet when it's done. You also have motion sensors, right? So things that sense motion, as the name suggests. Accelerometers are the big one that everyone in this room probably has in their pocket right now. Your phone has one in it. It's a sensor that measures orientation. So if you're, when you're turning your phone landscape to portrait, it can tell which way it's facing on 3 axes. Gyroscopes are similar to accelerometers, except they measure rotation. GPS obviously tells you where you are. Here's another cool one. This is the BNO 055 by Bosch. As you can see, this breakout, it's about the size of a quarter. On the picture on the left side, in the very center, you can see that black rectangle. That's the actual sensor itself. All of the stuff around it is the hardware that's necessary to make it easy to interface with. One of the main things we sell at Adafruit is these breakouts that make all these cool sensors easier to work with. As a brief side note, I work for Adafruit. This is going to be me shilling for them a bit. Not because I'm just a shill, but because Adafruit is a really awesome company, both to work for and to have in the community, right? They are an open source hardware and software company. They give away all the goods, right? If you wanted to build a Circuit Playground Express, you could go download the files, order the parts off of DigiKey, get your board from OshPark, and you could make your own, right? So it's I'm going to be shilling, sorry. So this is the BNO 055. This one's different, right? So it's got several sensors in it. It's got a magnetometer, measures magnetic field, so north and whatnot, an accelerometer, and a gyroscope. And it does sensor fusion on these things and will calculate all these different vector types for you, right? You just call out to it and say, hey, can I have a vector, please? And it's like, sure. Hey, here's your vector. Go point it at something. We've got wireless stuff, right? Who likes wires? No one. GPS, Wi-Fi, RFID, Bluetooth, aka BLE, all these things, they have modules that you can use to relatively simply go to Adafruit, read a guide. It'll show you what to plug into what, how to load the software, how to get a demo sketch going. I should mention that Adafruit is not alone in what we do. Another company that's very similar also makes really good products. They're our friends more than competitors, I would say. SparkFun. SparkFun was the first place that I ran into for selling electronics and stuff. They're actually responsible for me learning how to surface mount solder, which is a whole technical skill. So SparkFun is also a worthy destination for your monies. Cellular modules, what? Okay, we sell cellular modules. This is a shoe. I think someone messed up and it should be pronounced showy, but there it is. This is a cellular module. This is the Phona is the name that we gave to it. This is essentially all the phone bits of the phone, right? It doesn't have a screen or a keyboard, but you can attach a microphone, a speaker, and a microcontroller to talk to it, and you have a phone. You take your shoe, you add a Phona, and you've got a shoe phone, right? Who doesn't want that, right? Everyone wants a shoe phone. Other fun projects, you can stick some NeoPixels to the bottom of your shoe and a sensor to measure when you step, and you've got Firewalker sneakers. This is made by Becky Stern. She's big into wearables and all kinds of fun stuff. Great resource there. All of these projects I'm going to be showing you either have a tutorial on Adafruit or can be put together from tutorials on Adafruit. This is a LED harness bra thing that Amelia put together. So in the center, I don't know if that's a CPX or just a NeoPixel ring, but it's got NeoPixels all throughout it, and they're all individually adjustable. You can do that. It's just, come on, who doesn't want that? Right? I think I need to go pick one up. All right. I love this one. So this is Phil B's electronic demon costume. I told him I was going to be using this in my demo, and he was like, dude, that thing's super old. But it's super cool, right? Who doesn't want to be a neon demon-y thing, right? I am going to try and see if this works. I have a little brief video of what it does. Hopefully the sound works and the video works. It's not. There you go. He showed up on our show and tell one day and everyone was just cracking up. But yeah, that's there's a tutorial for all the bits that went into that on Adafruit. Interactive art, right? So you can say, hey, artist friend, I hear you're doing this cool art. I want to make it even cooler. Let's add some bits and bobbles to make it do stuff, right? Make it more interactive, make it not just sit there. I mean, don't get me wrong, art that just sits there is cool, but if it can move and do stuff, hey, why not? So you can add light, motion, sensing, movement, interactivity, all of these things. I like to say it gives your artwork senses and a voice, right? So you can make it see the world around it and interact with it. The best example of this I've ever seen, this guy is super cool. This is called Wooden Mirror by Daniel Rosen. It is a whole ton of little wooden squares, each controlled by a little stepper motor. And then it has a camera that can see what's in front of it, and it will adjust those pieces of wood to reflect or not the light around it, and changing if it looks light or dark. And this is it in person. So you can see it, dude, that thing's so cool. The same guy has also done similar stuff with pieces of trash, fluffy balls, penguins, whatever. He's just, that guy is super cool, super inspirational. So this is all cool, fun stuff, right? You know, making shoe phones and mirror things. But hardware doesn't just have to be all fun and games. It can actually do useful things, right? One of those really good and meaningful, helpful things is helping people that need it, right? So this is a quote from Bill Binko of ATmakers. He says, ATmakers.org is an experiment in solving problems in assistive technology using the skills and tools of the maker community. In short, we've seen the tools of open source hardware and software community that can be incredibly useful for people with severe physical and cognitive challenges. We'd like to help introduce these communities to each other. So if you're not familiar, assistive technology are pieces of technology that people with different abilities can essentially, I like to think of it, again, using the bridge metaphor. It's a bridge between how they need to interact with the world and the world around them, right? It just makes it better for them. And so you can contribute to that. You can, most assistive technologies are, private, closed source, but we're trying to change that. So I said break or demo. Which demo am I gonna give? I'm gonna skip the demo for now. So I have another one later. Hopefully I'll get to it. 32 of 105, oh boy. So datasheets, what is a datasheet? A datasheet is, as a hardware designer and software and firmware developer, that is your Bible, right? It's an in-depth technical document that covers just about everything about a piece of hardware. How big it is, what shape it is, what connections it has, what voltages it can take, how do you talk to it, like on an electrical level, what super in depth. One of the key things that it shows you is what the register layout within the device is. And what that is, I'll get back to it. They are always wrong, and quite often, there's just, depending on how much caffeine the person that wrote the data sheet has, you will have a bad or good experience, because sometimes stuff is just missing. So drivers, what do they even do? They take requests from the user, they read to or write from registers in the piece of hardware, and optionally return a result. If you're setting settings, it doesn't really need to return anything, but if you're asking for data, then you will. How do they even do this? Okay, so let's talk about what a register is. My note says diagrams need here. That would have been useful. I like to say a register is kind of like a memory for a possessed computer, right? So normally in memory, you have a chunk of memory, you say, put this thing in this address, and then later you come back and get it back, and it's the same as when you put it in there unless someone else messed with it, right? Registers are not like that. Registers are like memory in that they have an address that you read to and write from, but it's like, if you imagine memory is a bunch of drawers in a filing cabinet or something. Normally you put something in the drawer, come back later, pull it out, it's the same thing. This is like, okay, you put something in the top drawer. Say you put, a paper with the number 3 in the top drawer. Next drawer down, you put a cat, close the door, and pull out the third drawer, and there's 3 cats. Close all the drawers, open the first drawer, put a 1 inside, close it, open the third drawer, 1 cat. They do crazy things, right? You're not always going to necessarily get the same thing. But that's how they work and what they have to do to be able to do stuff, right? So like for a temperature sensor, every time you call the temperature register, it's going to be different because the temperature is changing. And there's my drawer metaphor. So registers in the wild, what are they like? They have an address corresponding to 1 or more bytes. They may hold a value, configuration state, or status information. Configuration state, if can be like the data rate that your accelerometer is measuring the acceleration. The faster you do it, the more power it's going to consume. So if you're in a phone or something, you don't want to do it all the time. A value would be your acceleration values. Status information could be like, are you done making that measurement yet? Yes or no? So Reading and writing bytes is the name of the game when writing drivers. You, yeah, let's move on. So I'm going to talk briefly about transports. Transports are like another name for the methods that embedded devices use to talk to each other, right? The corollary would be like HTTP is the protocol that we, and IP and all the stuff below it. The equivalents in embedded LAN are things like I2C. This is, I forget what it stands for. It's a protocol put out by Philips originally. It's got a single data line and a single clock line that is shared between both sides. SPI is a different serial protocol. It's got a separate clock line and data line, and then it's got a line each way for each direction stuff is traveling, and also a flag to figure out which device on the bus is talking. Also, UART is another one. This is your like old school serial stuff. You know, when you were talking to your modem, sending it AT commands or whatever. That's that. Lots of things like GPS modules still use UART to talk to them. Yep, so I'm not going to cover transports beyond what I just said. We're going to just imagine we have a magical transport. Yeah. Oh, wow. Cool. All right, well, so much for that. Thought I had 45 minutes. Okay, well, hang out if you want. I'm going to finish. I will go faster. And there's few enough of you that if you have questions, let me know when I'm going too fast. So, turbo mode. Don't have that example. So, going back to talking about reading and writing bytes, you can't write a single bit to a register. You can only write a whole byte or read a whole byte. But many things require you to just set a single bit, right? So like configuration bits or status information bits will say if a register is done or if a measurement is done being made. Similarly, you can use a bit to just toggle some setting of some sort. But sharing is caring. There's only so much space to go around. This is why they shove a whole bunch of different configuration things in a single byte, right? You don't need a whole byte to say yes or no. That's what bits are for. So you can't buy a single bun, right? This is another way of saying you can't go ahead and just read or write a single bit. You have to read or write full registers. You guys know bits and bytes and all that stuff. So when you're working with single bits, you have to do things a little bit different. First, you have to read in the current value. Then you have to modify it, only changing the bits you want, and then write the updated bytes. But how? How would you do this? How can you only modify single bits? Bitwise operations. We'll go through them real quick, trying. Hopefully this will be understandable. And it says for each bit in A and B, it compares them, and the new bit will be true if both bits are true. So here's a little table. So we're going from the right to the left. We've got a 0 and a 0. They are not both true, so we get a 0. A 1 and a 0. The one up top, still 0. Again, 0 because you've got a 0 and a 1. And finally, the moment we've been waiting for, 2 1s gets a 1. You can see there's a little bit of a pattern here. When the B byte, for example, had 0s, you just got 0s out. And when there were 1s, the 1 and the 0 from the byte A got transferred down to the original or to the resulting byte. This is useful. You can see that when there are 0s in B, the 0s win, right? Whenever there's a 0 in one of the things, 0s will always win. So it's going to be useful. Or are very similar, except switched a little bit. It's true if either A or B is true. It's applied to every bit. Here's another example. None of these are true. One of these is true, so you get true. This is also true because we've got a true and a false. And finally, 2 trues are also true. Another pattern here, we've got 0s this time in B, and they allow the 1 and the 0 to pass through. Similarly, these ones in B take over, they win, right? I only want a single button because my therapist says it's okay to be alone. So how are you going to do this? We need to specify which bits that we care about, right? We have this fun bit math that we can use, but how's that going to work? Bit masks, right? Bit masks are a way of specifying which bits you want to work with in a byte. Ones for all the bits we care about and zeros for the rest. Here's another example. So in this case, B is our bit mask. You can tell it's a bit mask because it's got a little mask on it. And so in that example, you saw that the 1 and the 0 fell through, which was what we were going for there. Okay, so one approach to making bit masks is to just find a number that has the bits in the right spots. So here, 1 is just 1. It's got a 1 in the 1 place in binary. Same in hex. I'm also including hex if you care. It's a little bit more compact. Binary is a little bit easier to think about, I think. Single bit shifted over a little bit. We have a 4 as an example. 3, a 1 and a 2 adds up to 3. So you've got a pair next to each other. 4 in a row. What's 16 minus 5 is 15. So you've got all the bits until you flip over to 16. 16 is the next place. Hex F, very useful. 6, similar. 240 is all the top bits. This is cool, but also not useful at all. Anyone know why? We've got a whole bunch of ones there, a whole byte's worth, right? So if you care about all the bytes, you don't need to do bit math, just write the whole byte. Here's a cat. I was Googling for confusing, trying to remember all these numbers, and this is what came up. So there you go. Isn't it cute? It's all like, oh, where'd it go? Oh my God, what? Okay, there's got to be a better way, right? Turns out there's other tools. Left shift. So left shifting X to the Y. What does it do? Shifts all the bits of X, Y places to the left. When you're shifting things over, you're vacating some space. Those get filled in with zeros. It can also be used to multiply by 2 to the Y, right? So if you add a 0 onto the end of your paycheck, you've increased it by 10 times and you will get fired. But that's because in base 10, our normal number system, you move up a power of 10 every digit over to the left, right? So you're essentially, if you add a 0 to your paycheck, you're shifting everything over. It's times 10. Binary is similar, except it's a power of 2 because it's binary and each digit only has 2 possible values. Cool, so here's a little left shift diagram. We've got a bunch of bits up top. We're going to shift X 3 spots to the left, and we will get something like this. So you can see those 3 bits, the gray ones top left, got shifted out. All of the blue ones on top shifted over, and some fun new green ones filled in. Right shift, same thing, other direction. If your boss shifted your paycheck over a digit, you'd leave and sue him for wage theft. Right shift, here we go, same thing. All the things in the top, the blue ones get shifted over 3 spaces, the gray ones go away, the green ones are newly coming along for the ride. All right, so you don't have to do that, right? You don't have to remember all these numbers. You can shift numbers around to make your own bit masks. This can be more intuitive in the sense that when you're looking at a data sheet and it's telling you need to change this bit, it's going to say it's 5 places over. So it's kind of a one-to-one correlation. It makes a lot more sense. And you can do things programmatically that way. So working with some bits, how are we going to do this now that we have bit math and all this fun stuff? We're going to read the current value. We're going to modify it using a bit mask and some combination of and or. Then we're going to write the updated bytes. So here's an example of reading a single bit. First, you read the whole byte. Then you want to create a bit mask by shifting 1 into the position of the bit that you care about. Then you're going to AND the byte and the bit mask. And the resulting value will be the bit that you care about. If the resulting value is 0, that bit you care about is false. Anything other than 0, it will be true, because since you've shifted it over to a higher place, the value you get back might be larger than 1. If you were to shift it back, it'd go back down to 1. So here is an example. What is this example? It's another example of AND. So we're masking the 2 top bits in what would have been B. And you can see that these 2 zeros I'm not sure what this is supposed to be doing. Bit masks. Right, yeah, so this is reading, right? So you're saying, what do we want to get out of it? We're bit masking the 2 top bits because those are the ones we care about. The rest of them, we've specified zeros in the bit mask so that we get zeros. Zeros fall through. Writing a single bit, same basic idea. Create a bit mask, shift it over. You OR the byte with the bit mask, and you write the updated bytes. Single bit diagram, didn't do that, oops. Yeah, I did. So what is writing a single bit to true? Oh, right, they're different. Right, so setting a bit to true and setting a bit to false are a little bit different. You have different approaches. So when you AND with a bit, the ones will win on an AND, so you'll always, for surezies, get the 1. If you want to write it to false, a little bit different. Again, doing all these things, reading the byte, shifting it over. In this case, you need to, instead of ANDing with the 1, you need to set all the bits, or in this case, bit you care about, to 0 by ANDing the byte with the inverse, or the opposite of the bit mask. And you're like, why, how, what, how do we do that? This is a bitwise not. It's pretty straightforward. It just toggles every bit in the byte. So if it's a 1, it becomes a 0 becomes a 1. Don't have that diagram. So if you're writing a single bit to false, again, read the byte, make a bit mask, set things to 0 by ANDing the byte with the bitwise not of the bit mask, and write the update. All right, reading n bits. Why would you want to read a number of bits? Quite often there's configuration options that have more than 2 options. So if you have more than 2 options, you're going to have more than a single bit to specify which option you care about. Each option will be represented by a number between 0 and n bits squared minus 1. And the bits must fit, right? So the number that you're setting has to fit within the number of bits that you're specifying. And so you select the option by setting the bits in the register to the appropriate number. Here's an example of that. So this is some excerpts from a datasheet for, I think this is a pressure sensor. So in the top, it's got the layout of the register. Bits 6, 5, and 4 are output data rate registers. So the combination of the 3 will get a value from the table in the bottom to specify the rate that measurements are being taken, anywhere from apparently 1 hertz to 75 hertz. Yep. So how are you going to read n bits? You read the full byte. You determine a number whose binary representation is a number of, let me say this again. You need to find a binary number whose binary representation is n1s. And then you create a bit mask using that by shifting it over. And here's an example of some multi-byte or multi-bit bit masks. Again, if you want 2, 3, or 4 bits, you can either do it in binary, decimal, or hex. And then you'll be shifting things around. So how are we doing this? We're reading the full byte. Then we're going to find X, where bin X is and ones, make a bit mask, shift it over, and then to read, you're going to be ANDing the bit mask again, like with a single bit, but in this case, you've got multiple bits, and because you don't care if it's true or false, you actually care about the number in there, you have to shift it back over to actually get the number you care about. So you'll shift it over some number, shift it back the same number. Writing some bits, lots of the same idea. You have to make a bit mask, shift it over. In this case, similar to writing, you need to clear out the existing bits by ANDing it with the inversion of the bit mask. And then you're going to shift the new value into place. And then you're going to set all the, that's out of order. So you're going to shift all the bits over once you've cleared them out by ANDing the bit mask with the opposite of it. Then you're going to shift the new bits into place and OR them to set them. All right, that's a whole bunch of stuff. I had to go too fast, but that's fine. How can CircuitPython make this easier? We have tools, right? So we have this library called register. What it does is it provides descriptors that manage all of the bit booping and bobbling, right? So it does all the bitmap for you. It's super cool, and I do have a demo for that. So for right now in CircuitPython, right now we only do I2C right now because SPI is a little bit wonky. It's got a lot of different ways that it can work, and most of the sensors, or a lot of the sensors we use are I2C. So it deals with the negotiating of the traffic on the I2C bus. Because it's a bus, there can be multiple things trying to talk, and you have to figure out who wants to talk when. And so the register library does that for you. You just say, send this, get this. It handles all of that for you. I'll have my slides up on GitHub. So this will be a link that you can follow to go to where the code is, and I will show it to you in a minute. That's ostensibly the end, except for one or two demos I can do if you guys are interested. Here's some resources you can use if any of the things I said are interesting to you. CircuitPython.org is the main site for CircuitPython. It's got everything from builds of CircuitPython that you can drag and drop onto your devices, resources for access to drivers, how you can make community contributions, all kinds of fun stuff like that. We also have a mal-formatted link here. Welcome to CircuitPython is one of our main tutorials. It goes from 0 to 100 in CircuitPython. It's super useful. I think that one was written by Katney, one of my coworkers. I am Sedacious on Twitter, Discord, the Adafruit Discord, and GitHub. So that's most of my talk. Sorry it was so fast. Thank you. Okay, so I'm going to try and do another demo. Let's go back to mirroring again. So, mirror. Yep, cool. Yeah, by all means.
So I've done embedded stuff, with mostly C.
Uh-huh.
The thing that always irks me when it comes to these drivers is that because you're working on a microcontroller, like you're either doing bare metal or you just have an RTOS, which means there usually is no generic device model. Like you have in Linux, you have drivers and there's block devices and character devices, or they have an ioctal interface. You talk to these things the same way. Like from what I've seen, that usually doesn't exist in the world of microcontrollers. Does CircuitPython have that?
The closest thing we have is the register library, right? It makes it, I'll show you some examples in just a second. It is as close to uniform as possible, right? Because every single piece of hardware you know, whatever the engineer came up with, it's going to work differently, right? Exactly, yeah. And we also have essentially ported register over to Arduino because it's really cool and it works really well. So we've got another thing that does, that one does SPI as well. If you're interested, come talk to me. I'll show you some more about it. So here's my other longer demo. Thanks for hanging out. This is the data sheet for this little guy, the little guy on the end of the string here, this guy. This is a VCNL 4040. It's a proximity and ambient light sensor made by Vishay. So we're looking at the data sheet here. We're going to write a driver very quickly. Spoiler alert, I already wrote it. So here we're looking at all the registers. So most data sheets will have, well, they have to have this. This is a list of all the registers. Far to the left, you've got the address that it's at. This particular device has, each register has 2 bytes, so it's got a high byte and a low byte. For our demo here, we are going to look at, let's see, number 3 over here. It's got the high byte here. Is it high byte or is it low byte? PS enable disable. So this is PS is proximity here. So byte number 3, remember that number. It can enable and disable the proximity sensor. And if you're going to do stuff with proximity, you want some data coming out of it. So at address 8 is the low and high bytes of the proximity data. Cool. So what are we going to do with that information? We are going to go over to Moo and plug in our little guy. So what I'm doing this with is it's called a Itsy Bitsy M4. M4 is designating that it's got a Cortex M4 processor in it, 120 megahertz, overclockable to 200, I think. Lots of RAM. A lot of our new devices are M4 because they have a lot of memory on them. And as you might guess, CircuitPython likes lots of memory. So what do we have here? Let's open up some stuff. So here's CircuitPython, right? So you can see on the left here, I've got my CircuitPy drive. It's just showing up like a drive. And this is all the stuff I have on it right now. Your code.py is like it's like your main, right? So if you have a code.py or coincidentally main.py, that will be automatically run when the device boots up. In this case, I am going to, actually, yeah, this will probably be better. I've made a mini driver. So this is minimum viable driver for this thing, right? So up the top, we are importing different descriptors from Adafruit register. We've got, and we were also importing the I2C device. That is the bit that does all of the bus negotiation for you. So you can see in the init on line 10, we're being passed in an I2C and optionally an address. So here we're going to make that I2C device. We're doing that here because register expects self to have an I2C device. So here is the nuts and bolts, right? So this is how you make a thing to shut down or not the proximity sensor. You say I have a read-write bit at address 3, shifted over 0 spots, and the register is 2 bytes wide. Similarly, we need one for the proximity value. So at address 8, we're saying we have a, what is that, little endian short. This here is a format string that you would shove into struct. Unpack. So unpack, pack into. These are all super useful in embedded land because you're dealing with bits and what so much. Cool. So that's all it takes, right? So what is this? 13 lines of code if you ignore all the libraries. Let's see how this works. So can you guys see the whole thing? Yeah, cool. So one great thing about Moo, it automatically installs really easily. It's kind of like just set it and forget it. It's not a full-fledged IDE, so it doesn't have all the bells and whistles that you would want, but it's super useful for stuff like this. So it's good.
It's not the Arduino IDE.
No, but it's similar. It's kind of, yeah, it's probably certainly inspired by it. It kind of just works. You know, if this is your first example of doing something like this, it's got all the things you need, right? So one of them is this here. This is the serial REPL. So the sketch I have on here right now, I can actually, well, I'll save the other demo for later. It's even more cool, but I'll come back to that. Actually, I don't know if I have Wi-Fi here. So yeah, so this is, what you're seeing here is the standard out from the currently running sketch. It's getting errors because the piece isn't plugged in, but if I Control C, we drop out to a REPL. The REPL will show you which version of CircuitPython you're running. Apparently I'm still running the RC, I should update. And it says what you're running it on, itsy M4. SAMD51G19 is the specific chip that is on the itsy bitsy, if you are interested. The SAMD line is one of the main things that Adafruit puts on boards. So on the device, I also have something to use this driver I wrote. I believe it is called Mini VC. Open Sesame. That just crashed. Awesome. So Moo crashes sometimes. Oh, or just moved. My bad. Sorry, Moo. Not your fault. Gonna open this here. Okay, so this is the piece of code that's going to be using our little driver importing board to get access to all the pins and whatnots. Mini VCNL 4040 is our little driver here. And here we're setting up the I2C bus. Board also includes a default bus. So there's default I2C pins, SPI pins, UART pins. And if you're using some of those, we have these objects for them built already. So you can just say board.I2C. Then we're passing that into our little driver, and we are going to run in a loop. So I am going to see if this works. NEVC, typos. Cool, that's a bunch of numbers scrolling by. I'm gonna close this and head over to Arduino land because I like the plotter there a little bit more. And serial plotter. All right, we got some values. Insert a little sensor here. Let's make it do things. Oh, look, I'm moving it closer and farther and the values are changing. It works, huzzah. So that's it, right? That's CircuitPython, that's register. Apologies for being so rushed. This was my first time speaking and I didn't know what I was doing apparently. So, any questions? Yes?
I have lots.
Cool.
With CircuitPython, can you define interrupt service routines?
Not currently. MicroPython has interrupts support. In the core C code, it's obviously there. We need to do it for lots of internal stuff. We don't have them yet because we're trying to figure out if interrupts are the best way to do concurrency for new users, right? Trying to explain interrupts, priority inversion, all these things to someone who's never programmed before, once they get to the level of needing an interrupt, needing to, being able to juggle and chew gum at the same time. We're not yet convinced that interrupts are the best way to do that. There's a GitHub ticket open to figure that out. There's lots of discussion going on there. There's all kinds of different ways we could do it. So we haven't.
Similarly, do you have asynchronous operations? So like if you're reading 100 bytes, my squared C, can you say start it?
Same thing. That's the same conversation, basically. Whether or not we have an asynchronous thing, yeah, it's the same thing, right? So if depending on how we do it, that will fit both of those boats, right? It will probably not, if we don't have interrupts, it's going to apply in both cases. But we will have some sort of concurrency eventually.
So looks like you're using
Right. Mm-hmm. Yeah, so, I mean, at this point, the people that are still here are cool beans. Yes, actually. Yeah, so the way that we decided to do Wi-Fi in a lot of the Adafruit products, where did it go? I'll come back to that, is we essentially have boards with ESP32s on them running Nina firmware that exposes the SPI interface, and then the ESP32 does all of that stuff for you, right? There's a simple interface for opening sockets and reading to and writing from them. So some of that stuff is, there's probably some asynchronous stuff handled by the ESP32, maybe not, I don't know. Yeah, does that answer your question at all? Right. So I blazed over that spot. We forked because we have different goals. This is the main thing, right? It started off with Lamore, Lady Ada of Adafruit fame, talking to Scott, who's now the lead contributor on CircuitPython. She just wanted to get MicroPython running on the SAMD21 and, well, there wasn't SAMD51 at the time. She just wanted to port it to this cool microcontroller that she found. She hired Scott to do it. In the process of doing so, they realized that the goals of MicroPython weren't quite in line with what they wanted to do, right? It's, to my understanding, MicroPython has different APIs for different types of hardware, right? So the drivers are not portable. So CircuitPython doesn't have that. We have a standard interface for all of the different types of hardware we support, so our drivers will work with whatever. That was one big thing, but also just we do a lot of effort to keep it in line with CPython. So hopefully anything you write in CircuitPython is actual legit Python you can run on a Raspberry Pi or whatever. In fact, we have a compatibility layer for single board computers that allows you to use CircuitPython libraries with single board computers. I think 3.7, I don't honestly know, but 3 something, yeah. No, not yet. There are things in the works that will do something along those lines, but it's super, super not even alpha yet, so I can't really talk about it, but if you come to me, I'll whisper in your ear. It's really not a big secret, but does that answer your question? Yeah. One thing I forgot to mention, a big difference between CircuitPython and MicroPython, where did my display go? There it is. I'm gonna go over to, hello, there it is, CircuitPython.org. One big difference, so this is CircuitPython.org. You're going to go here all the time if you get into CircuitPython. One of the big targets here is the downloads page. We have, these are all the boards that run CircuitPython, right? Obviously a bunch of Adafruit boards, but as you get down, there are more than a couple that are not Adafruit. So the Arduino Zero also has a SAMD51. Basically anything on this page, if it has a SAMD21, 51, or NRF 52840, you can run CircuitPython on it. Ideally, it will have some external flash and a NeoPixel to have a little bit better of experience, but I just counted on the way over and there's some 67 boards we support. If you have a SAMD21 board or SAMD51 board or NRF board, we can help you get it running in CircuitPython.
There's like no package manager for this, right?
Nope.
You just copy
Yeah, so
into your project, and that's how you get a lot.
right, yeah, that is something we have to tackle because we do have some dependencies that we have to worry about. Not so crazy that, well, basically it's we're gonna do some tooling to make managing libraries and all that stuff a little bit easier, but it's early days. The way we distribute all of our libraries is in what we call a bundle. So we have this automated process that takes all the repos for the drivers, compiles them as MPIs, which are basically the bytecode for the Python that you're talking about. So it takes up less space on your flash drive. So these are just huge packages of the MPIs of all of the drivers we support. And so if you have something like something with an external flash chip, like most of the CircuitPython Express boards from Adafruit do, you just dump all of this onto your CircuitPy drive and you're ready to go. You don't have to worry about it.
So the bytecode is more compressed than if you were just plopping.
Right, it's binary essentially instead of text, right? It's done all of the parsing and whatnot to turn it into bytecode already. Yep. Cool, thank you. I'll be down at the thing if you want to hang out and talk hardware. I've got some other fun stuff. Oh, hey.